really need to. I put a sticky on myself to do that. Okay, so we're starting into week 2, and I sent an email out earlier today that describes some of the things you can expect in week 2. So we have our homework that's already posted, our extra credit that's already posted. The quiz will be handled like it was last week. So it'll begin on Thursday at midnight, and it'll end at 2 p.m. on Friday, so that you have 24 hours from the start of class on Thursday. So you have time with that quiz. So you'll have that. And then over the weekend, once grades come in, I'll sync those with our grade book. One student asked about the grades that are in the grade book. You may be seeing, it's quite likely that you're seeing a grade of nothing over nothing, meaning like seemingly like you have nothing turned in. And that is not true. Because the lowest of your quizzes and the lowest of your homeworks are dropped, it may, right now, whatever you have on that quiz or homework is the lowest that you have. And so they will, it's automatically dropped until your second one pops in. If your second one's lower, that gets dropped. If your second one is higher, your first one's still dropped. And that'll continue till the end of the semester. So what your lowest is may change throughout the course of the semester. And at least right now, the way the grade book is configured. That iPhone. Oops. So anything over 100% isn't recognized. And so, but once actual grades pop in, all of your extra credit will be there and posted, so everything should be fine. But if you have questions like that, please do feel free to email me or contact me. I'm happy to make those things clear to you. I know grades are something people are always watching, so I'll keep those in mind. Now, I'll start PowerPoint so that we can start to go through some of the content for today. I did post 2 videos so far, and some more will be coming based on the content that we have. So for this week, we're doing basically atoms and molecules. So we'll be stopping probably just shy of some real stoichiometry. We might get into it a little bit. But I expect that we'll get into, so today we're doing periodic table and nomenclature, and atom and mole and gram conversions, so all that good stuff. And then on our second meeting of this week on Thursday, we'll be getting into actual molecular formulas, which usually involve things like empirical molecular formulas, combustion analysis. So I'll send out some problems in advance of that, so they get an opportunity to try some of those problems out. And yeah, and I'll also send an email out tomorrow telling you what you can expect on the quiz. So all those things should be pretty straightforward. Now, I'm going to go into the PowerPoint, so I'll start sharing my screen here. Okay. Put on this laser pointer. Minimize this. Okay, so if you have any questions or anything, please feel free to address them in the chat. I'll be taking a look at that. We'll take little breaks as this goes on. So this is class for today. And we'll start with subatomic particles. Periodic table, atomic mass, those are actually sort of intertwined. Moles and conversions for those, classifications of pure substances, and then we're going to go into nomenclature. We'll stop at binary ionic nomenclature, and then I'll do videos for polyatomics and for molecular nomenclature. So we'll go in there, because otherwise this was getting to be a bit of a hodgepodge, so I wanted to sort of stop it at that point. But let's go into some stuff. So a video that I posted previously kind of goes through some atomic history, how we got to know that there are atoms that contain protons, neutrons, electrons. And you've heard some of these stories before, so I don't feel the need to go into them in this part of class, but I posted another video to talk about them. So please do take a look at that, because it is still important. But it arrives at this little bit of knowledge that we have protons, we have neutrons, we have electrons, and we have the 3 things that make up an atom. So an atom is the smallest unique division of matter. It is not the smallest division of matter. It gets smaller, but it's the smallest unique one, because when we have these atoms, neutrons, and electrons combined, they make an atom, and that atom is unique to one element. And so once we get down smaller than that, a proton can be a proton of anything. Or the combination of protons, neutrons, and electrons is one particular atom, and that's what's unique. So let's admit Alex. So protons and neutrons, they have nearly identical masses. You can see them over here, 1.672 times 10 to the minus 27 kilograms, and neutrons 1.675 times 10 to the minus 26 kilograms. There is a mass known as the atomic mass unit that we don't really do anything with, but this sort of allows us to deal with these in numbers that aren't so tiny, right? I mean, while protons, neutrons, and electrons all have mass, it has mass that will never show up on a scale that we can. Electrons, they have a very small mass, roughly 1/10,000th of the mass of a proton or a neutron. So if an atom loses an electron or gains an electron, its mass does not change really at all. They do have relative charge with one another. So a proton has a relative charge of +1, a neutron has no relative charge, and an electron has a relative charge of -1. And that charge is quantified in coulombs. Again, this is a number we don't do anything with. In physics, they do an awful lot with this. We'll do a little bit with this in second semester chem if you're going to take 26. So you can expect to see some of it there. But a neutral atom, and this is important to know, would have the same number of protons and electrons. So for every positive charge, it would have a negative charge, and the sum of those would be the total charge of the molecule. And if the molecule is neutral, or atom is neutral, then it would have the same number of protons and electrons, the same number of positive charges and negative charges, making it neutral. So you see elemental symbols like this all the time on periodic tables. I posted a periodic table that I'm used to using. It's the one that would normally you'd be given in a class like this if we were meeting face to face. And the one that I give out has names on it. So just one quick thing to be clear on is I do not expect you to memorize the names of elements on periodic tables with the elements. They are everywhere. I have them on blankets, socks, ties, shower curtains, towels, all kinds of things. And there's no reason to memorize these names. The more you use it, the more you just sort of know them, but these are always easy things to look at. So carbon, this element being shown right here, C is for carbon. This number right here, this 6, is what's known as its atomic number. It corresponds to the number of protons in its nucleus, and it is unique to its identity. So every carbon atom, no matter what its mass is, has 6 protons in its nucleus. The atomic mass down here, this mass number, 12.011, that's the mass of 1 mole of carbon atoms. So it would weigh 12.011 grams. We'll get into what a mole is later. And this mass, 12.011, applies to groups of atoms, not individual ones. So a single carbon atom does not have the mass of 12.011. That is just one atom. It will not have that mass. A mole of atoms would have that mass. Okay, and that has to do with relative abundance, which we'll get into in the next slide. Isotopes are 2 different atoms that have the same number of protons. So here's carbon with 6 protons, here's carbon with 6 protons. And they have a different number of neutrons. Now this sort of nomenclature, after this chapter, you don't really see all that much until you do nuclear chemistry way at the end of second semester. But it typically goes, if you imagine there's a side to this, so there's carbon, and then on the left-hand side, there's room for 2 numbers. The top number is always the mass, the bottom number is always the atomic number. So mass of 12, an atomic number of 6. Mass of 13, atomic number of 6. So the difference between these 2 numbers is the number of its neutrons. So this is a carbon with 6 neutrons, and this is a carbon with 7 neutrons. They have the same number of protons, so they're both carbon, but they're different isotopes of the same element. Okay? And notice that this is not 12.011. This is the sum of protons and neutrons in the nucleus of this atom. Okay, so that's only good for atoms, not for groups of atoms. Now, the atomic mass, the one you see there in the periodic table, it's based on relative abundance. And so what you're seeing is an actual weighted average of all the different isotopes that exist. So for any one atom, there could be more than one isotope in existence, and for most atoms there are. So carbon, for example, has a couple of stable isotopes, actually a third one as well, carbon 14. But 98.9% of all carbon is carbon 12, and 1.1% of all carbon is carbon 13. Carbon 12 would have 6 neutrons, carbon 13 would have 7 neutrons. And so if I took the mass, 12, which represents 98.9%, and I added it to the mass 13, which represents 1.1%, the sum total of those things, which is called the weighted average, comes out to what we recognize as the atomic mass, the 12.011. And that becomes important when we're talking about things like moles. So a mole of anything contains 6.022 times 10 to the 23rd of that thing. Right, so a mole of atoms is that many atoms. And that number of things would be considered like a pretty good sample size, so a good representative sample. So if I had 1 mole of carbon atoms, and I've got 10 to the 23rd, different things contributing to that sample, I could say that that's a representative sample. And this sort of distribution is shown in that representative sample, and so that's what allows me to use these mass groups. The mass in the periodic table refers to the mass of 1 mole or mole of atoms, and collections of isotopes in their various abundances will contribute to that. So different atoms, like barium, will have 2 isotopes, which are bromine will have 2 isotopes, which are roughly 50% each. Other ones will have isotopes that are 25%, 75%, things like that. There's a couple of things in your book that deal with relative abundance. We don't do that math. It's there, and this is all of that I'm going to go into. There's no reason for us to do more of it. It's just a simple algebraic trick that you pick up in this chapter and then never really using it. So we're not going to go into that in great detail. But for individual isotopes, there's a few things that we want to pay attention to. There's the atomic number, which we know is the number of protons, the atomic mass, which is the sum of protons and neutrons, and then its electrical charge, which can have 3 different ways of being represented. If it's a neutral atom, the number of protons and electrons, those are equal. Okay? So I've got the same number of each, and their relative charges cancel out, and so it's a neutral atom. If I have a cation, it means I have more protons than I do electrons. So that means that this is something that lost an electron, not necessarily gained. If it gained a proton, it became a new element. So if it lost an electron, it did not become a new element, but its charge changed. It has some kind of positive charge. So that is pronounced cation, and that's what we recognize there. Its opposite is the anion, and that's where it has gained an electron. It has not lost a proton. Losing a proton would make it a different element entirely. So it simply gains an electron. So here's an example of something that's neutral, or shown to be neutral. So this is chlorine, atomic mass 35, 17 is its atomic number, and there's nothing in the upper right-hand corner that says anything plus or minus, so this would be taken as a neutral atom. This is an example of a cation, where I've got mass number 39, 19 protons, and it's got a plus charge right here. So what that means is that this has it's a cation, and it has more protons than it does electrons. And the anion right here, it's got 17 protons, and it's got a mass number 35, so it has 18 neutrons, and it has this negative charge right here. So if there's no number next to this, it's taken as 1. So this would be potassium plus 1, chloride minus 1. Okay, if there's a number like 2 or 3, then that's what the number is. So we can look and see the number of protons, neutrons, and electrons that this has. And for the first one here, 17 protons, because that's that number here, 17 electrons, because it's neutral, and then 18 neutrons, because it's the difference between these 2 numbers. Potassium, same thing, 19 is this mass number here, or atomic number. It's got a plus 1 charge, which means it has fewer electrons than protons, so that's 18. And then the difference between 19 and 39 is 20. That must be the number of neutrons. With protons, it's the same kind of thing. For the last one, 17 protons for chlorine. It's got a negative charge. It means it has more electrons than protons, so it has 1 more electron than protons. And then the difference between these 2 numbers is 18, and that's the number of neutrons. Okay? So this is a common exercise. I partially filled out a table here, and you should be able to fill out the rest. Now this is this entire PowerPoint is in our My Courses page now, and you can sort of look at it if you want. You can print it out and see if you're kind of copying along. I'm going to give you, let's say, like a minute. Now, I do not expect you to complete this entire table in a minute, but maybe you can complete like the first 3 in 1 minute. What your job is to fill in the numbers that are blank. Okay, so I've given you enough information to figure it out, but I haven't told you explicitly what all these are. So I'm going to give you like a minute to try this out. At least get the first 2 or 3 done. And then it's started. You should definitely try this. Not the copy. Copy pretty bad at this point. About 5 seconds left. Okay, so just looking ahead here and putting in red, copper. If you're looking at a periodic table, and I printed and I gave you one, copper is element 29. So that means if you know the element, you know how many protons it has. I gave you its mass, 64. The difference between 29 and 64 is 35. You know how many neutrons. I told you its charge was +2, which means it must have more protons than electrons, so it must only have 27 electrons. That same logic is applied through here. Here I give the number of protons, but not the element. So if it's 16 protons, it must be element 16, which is sulfur. The sum of these two numbers is its mass, 32, and it's got a charge of -2, which means it must have more electrons than protons. Same thing here with krypton, same thing here with chromium. And this is the one that I usually throw in because it slips people up. If I put in 1 proton, 1 neutron, 1 electron, people often very quickly say that it's hydrogen, but they say its mass is 1. And at least in this case, this is not true. Remember, this is for individual atoms. So this would be for the isotope of hydrogen, which contains a neutron, which is a real thing. It exists. It's often referred to as deuterium. So its mass is 1 + 1, which is 2, not the mass that you see on the periodic table. The mass that you see on the periodic table is not the mass that goes in here. This is the mass that comes from the sum of protons and neutrons. Please be clear on that. Common mistake is. Okay, we're here, we have a periodic table, so in class I'd be making a big show of this in face-to-face class, that is. So here, this is the class that we have. A bunch of these elements were known for just a really long time, before 1800. That's because we were making things with a lot of these elements. We knew that they were different from one another. So in light blue, they sort of represent those. And then some of the darker ones we were able to find or isolate through a number of ways. And then from 1950 on, that is the Manhattan Project era, or the nuclear race. And that's when we were able to start producing elements pretty much at will, filling out this part of the periodic table. One of my favorite things to do is to go around and take pictures of one of my favorite things to do is walk around and take different pictures of the periodic table because they're different in different places, and they were, depending on the year they went up, they're going to have the different numbers of elements on there, the right ones that or the names that they've posted on there. And if you're a fan of Stranger Things, you know what a period piece that is for the 80s. They got the wrong periodic table on the wall there, so that's something I. One of the elements that I sort of wanted to point out here is polonium. So all these elements have different stories. Polonium is one of the ones that I really like to talk about. So this was discovered by Marie Curie. She isolated it from samples that contained uranium or pitchblende. And this was one of the first things that she discovered when she was looking into radioactivity. The other element that she discovered was radium, and that's what she got a Nobel Prize for. But polonium was the first one that she came up with, and it was more or less, hey, that's great, but kind of overlooked. There's no real uses for it. It's in such trace amounts. It's actually really quite poisonous when you get down to it. At any rate, so polonium is the element that we have right here, and her given name is Marie Slawska, not Marie Curie. When she became Marie Curie, she had moved from her home in Poland over to France, and she was going to school there. When she made that move, Poland as a country didn't really exist, and it was part of other countries, and that's happened to Poland over its history. It was part of Germany for a while, part of Ukraine for a while, Russia for a while. So polonium, as an element, is one of the only elements on the periodic table that has been named out of political protest. It's absolutely, it's really kind of cool for that reason. Please excuse me for a second. There's something at the door. Sorry about that. It rang like 3 times. Okay, so other elements that are on here is kind of neat. Seaborgium, this one right down here, Sg. That is an element that was named for Glenn Seaborg, who is really largely responsible for putting like all of these on the periodic table. And so they named this element after him. But the odd thing was that he's one of the few living people to have an element named after him. So and there was quite a fight over that. And I got to see him once at a conference where he was wearing a T-shirt that said, "I'm in my element," Glenn Seaborg. It was really just quite very, very nice. He ended up dying, as many older people do, after a fall that he was never able to recover from. He was a very sweet old man. So there are general regions to the periodic table that we need to pay attention to. The vast majority of things on the periodic table are what we would call metals. Now, metals does not mean solids, but they are metals. So most of the metals on the periodic table, they're covered here in this sort of beigeish color. And metals all have these things in common. They are ductile, malleable. That's two things people often throw out. So ductile means you can pull it into a long wire. Malleable means you can pound it flat into a sheet. When they undergo chemical reactions, they tend to lose electrons. They're lustrous, that's not on this list, but they tend to be shiny and reflect light in most cases. And they're good conductors. That is, if you give them electricity or heat, they'll move it on. Okay, they won't heat up as much as other things because they tend to move that heat around. So these are all good conductors. And those are all properties of things that we would call metals. Non-metals are things that take up this area of the periodic table over here. Now, again, non-metals does not mean non-solid. There are plenty of solids and liquids in here. So bromine is one that is a liquid or temperature. Iodine is a solid at room temperature. You know, sulfur and selenium, both solids at room temperature. So these are all things that are non-metals, and they're the opposite of metals, which means they're brittle instead of being ductile and malleable. So that is, instead of changing shape, they'll break. They tend to gain electrons in reactions, which means that the charge ends up going down, becoming negative. And instead of being conductive, they tend to not pass heat or electricity on. They tend to be very insulating. So things that are between those two, these are not absolutes, are called metalloids. And basically, if you draw a line down boron and under it, down silicon and under it, down arsenic and under it, tellurium and under it, down astatine, things that are touching that line are what's known as metalloids. And those metalloids have the properties of both metals and non-metals, which means they can either be insulators or they can be conductors under given circumstances. Silicon's a great example of that. It works as a transistor, which means it can be conductive or not conductive, and that's what's responsible for all of the little microelectronics that we get to use, which is just fantastic. So those are the general regions of the periodic table. Now, groups on the periodic table are things you want to pay attention to. This is, again, something out of your book. I've doctored it up a little bit. So going from left to right or right to left on the periodic table this way, this represents a period. Okay, so this would be second period. This would be third period. Going up and down on the periodic table is what's known as a family or a group. So periodic tables often have these 1A, 2A, 3B, 4, and so on. These groups are numbered. So group 1, group 2, 3, 4, 5, 6, 7, 8. And then just counting from left to right, we've got all these different groups here. And the important thing for us to realize is that if you have things in the same column on the periodic table, that means that they're in a family. And if they're in the same family, they have the same kinds of properties. Now, the person who gave us this table, or credited with giving us this table, is a guy named Dmitry Mendeleev. And one of the things he used to do is he'd play a little game with himself. He'd lay out all the elements that were known, arrange them by alphabetical order, or other things that were known about them, until he saw some sort of pattern. And that's what allowed him to arrive at the periodic table. Other people were doing the same thing at the same time, and Dmitry Mendeleev is sort of like the one who kind of beat them to the punch and also documented it the best. And so he gets credit. There are some groups that I'm going to want you to know about. Okay, so this first family right here, from lithium on down, hydrogen is not really a part of this group. Hydrogen kind of belongs over here on the periodic table between the high boron carbon nitrogen. So from lithium on down, these are known as alkali metals. Lithium, sodium, potassium, rubidium, cesium, francium. They all tend to lose one electron when they go into a reaction. And sodium is a very soft metal. You can cut it with a butter knife. Okay. So they all tend to lose one electron, which means that when they undergo chemical reactions, they all have a +1 charge after they lost them. The next group here, to the left to the right of it, are alkali metals. And these metals all tend to lose 2 electrons when they undergo chemical reactions. So beryllium, magnesium, calcium, strontium, barium, radium, they all tend to give up 2 electrons. Skipping all the way over to the other side of the periodic table, you've got the halogens. So these are fluorine, chlorine, bromine, iodine, astatine, and tennessine. And they all tend to gain just 1 electron when they undergo a chemical reaction. So these are nonmetals, so instead of losing electrons, they gain them. Next are the chalcogens, and these all tend to gain 2 electrons when they go into the periodic table. And then these are noble gases. They tend not to undergo chemical reactions. They're known as inert, and that's because they have the electron configurations that they want, and there's no energetic benefit to them to gain or lose electrons. There are some common charges for things in the periodic table, and I think I'm going to repeat this slide later on, but just to sort of reiterate, this first group here, they all lose 1 electron. Second group, they all lose 2. Third group, this group over here, they all gain 1. Here, these all gain 2. These, nitrogen and phosphorus, they gain 3. Aluminum tends to lose 3. And then we'll see some others that go along with this as well. Pause there for a quick minute just to see, are there any questions over any of that? A lot of it is sort of surface level stuff, but I know it's stuff you've seen before, and if you took 1025, you may have seen a lot of that. So I just want to see if there are any questions and then you can use that. Looks like nothing's coming up there in the chat. No questions. One thing I'm gonna share a quick screen with you. So if share screen. Okay. So it should be sharing a screen here. So if you do a search for the world's largest periodic table of the elements, you'll come up with a number of images that look like this. But this is this one is mine. So the third one in here, this one's mine. This one up in 2006, September 22nd, 2006. And if I click on that image, you'll see this is Daly Plaza in downtown Chicago. Each of these windows is 9 feet wide, 9 feet tall. And so I hung a poster in each one that was 8 feet wide, 8 feet tall. So I made an 8-story periodic table of the elements. I raised about I don't know, $110,000 or so $110,000 to do it because it cost about $75,000. And it was a really awesome experience. And if I click on that, I'll go to the website of the person who put that up. Because the other really neat thing I'd like to show you is that after putting up that periodic table, I celebrated because it went up on September 22nd, which is my birthday, and that was the day I turned 30. So I ended up getting a tattoo of zinc there on my left shoulder because zinc is the 30th element. So a lot of people love things like their families and puppies and stuff, and I think those are just great. But I really like the periodic. So I hope you enjoy that. All right, share my screen again. Go back to this. All right. So now we are at moles, atoms, and grams. And one thing I want to point out is that these are 3 different ways that we can go at measuring and counting. And so atoms are very small. right? There's no scale in the world that we can use to put a single atom on and then see what it weighs the same way you would step on a bathroom scale. So what we tend to do is we tend to count these atoms in really large numbers. And the number that we have descended on is the mole. This is a number that was developed and discovered sort of by Amedeo Avogadro, I believe. And 6.022 times 10 to the 23rd is that number. It's an enormous number. It's got 23 zeros in it. But it is a number that has a name. That is a number, the mole has a name. Same way 12 as a number has a name of a dozen. Same way that 144 as a number has a name of a gross, which is a dozen dozens, 12 squared. So if we're talking about a mole of anything, it's 6.022 times 10 to the 23rd of that thing. One of the things that I posted to my courses is a little website from XKCD, Randall Monroe. Folks around here, he does those really kind of funny stick figure science things. So you should check him out. Don't be a casual observer. Don't be a casual participant in the sciences. Actually get into it. He writes really good, funny stuff. And he said what would happen if you had a mole of moles. So you want to check out that article. So anyway, 1 mole of atoms is 6.022 times 10 to the 23rd atoms. And one of the things that does is that gives us the mass of an atom on a periodic table. So that's a gram per mole conversion. That means that I have 1 mole, if I have 1 mole of carbon atoms, that's how many atoms I have, Avogadro's number. And it is equivalent to the mass of 12.011 grams. If I have a mole of aluminum atoms, I have the same number of atoms, 6.022 times 10 to the 23rd, and that's equivalent to 26.98. So this concept of a mole is a rather important one to us because it tells us not only how many things we have, but how much it would weigh. And the lighter an atom is, the less a single mole of it would weigh. So a mole of hydrogen doesn't weigh very much. A mole of uranium weighs a lot. So this is an important concept for us. Now what we do is we use it for conversions. That was supposed to be. So if I have 1 mole, 1.26 moles of iron, I want to convert that to grams. First thing I do is I sort of write out what I'm given. 1.26 moles of iron. I want to convert it to grams, which means my unit of moles will go on the bottom. The unit of grams is going to go on top. These two are going to cancel. And now I need to put the numbers in there that will do that. So 1 mole of iron has a mass of whatever the mass is on the periodic table, which is 55.85 grams. And when I go through and do the math, 70.4 grams is what I come out with. This is what my calculator gives me. But I start with 3 significant figures. I need to end with 3 significant figures. The rule of thumb is if you have 3 sig figs going in, try and take 4 from the periodic table. If you have 2 going in, take 2 or more, take 3 or more from the periodic table. Just trying to have more numbers in the constants you use than what you're given. Okay, so this is a rather straightforward way. All the conversions we did before were powers of 10 conversions. This is not anymore. This is new. If I wanted to convert 3.5 grams of phosphorus into atoms, it's the same process. So I've got 3.5 grams of phosphorus. I want to get rid of grams and turn that into moles, but I actually want atoms. So moles should not be my final answer. So I need another conversion factor, one between moles and atoms. And I luckily have that conversion factor. So 3.5 grams. Every mole of phosphorus weighs this much in grams, 30.97. Every mole of phosphorus also contains this many atoms, 6.022 times 3rd. So multiplying across the top, dividing by everything on the bottom, gets me to 6.81 times 10 to the 22nd atoms. Now, does this number make sense? Well, it's smaller than Avogadro's number by a factor of about 10. And this is smaller than a mole of phosphorus by a factor of almost 10. So yeah, this number makes sense. Same thing with the number over here. 1 mole of iron would weigh 55 grams. So more than a mole of iron should weigh more than 55 grams. Makes sense. So you want to go through and do that. Don't just trust what you get out of your calculator blindly. Try to actually look at it and say, all right, I did this, and the number I got fits within the realm of possibility. Okay. All right, so that ends really the second chapter there in Tro. Take us a quick break here. you guys have any questions, anything you want to ask questions on, discuss, or anything like that? There is a video on our class website that does more with converting things with grams, atoms, and moles. And because we can do it with any mass, we can use kilograms, micrograms, things like that, because you know how to do that metric conversion. We don't just have to use grams. Okay. So the last little bit we have to go into is classification of pure substances. And we're going to use binary nomenclature for that. So the third chapter, intro, gets into things that make molecules. And one of the ways in which that happens is with an ionic compound. Now, there's a really cool video by a guy named Theo Gray who I'd like to introduce you to. He writes a lot. He had the very first real big hit app ever on the Apple App Store, or whatever they call it, Google user. But they, anyway, his beautiful book of elements, they turned into an app, and it was just a runaway hit. So, and that's just his passion for chemistry there. So one of the things he did is he made sodium chloride, which is the salt that you see here, from atoms of chlorine gas and sodium metal. So he heated up sodium metal, he ran chlorine gas over it, and then the smoke that comes off is sodium chloride table salt. I'll put that video on your class website. It's a really cool thing to see. At any rate, the way that this happens is a neutral sodium atom will end up giving an electron to a chlorine atom, becoming chloride. And then the two of these things, now you have a positively charged thing and a negatively charged thing, they become attracted to each other and they form this lattice. And that attraction between the two of them is what's known as an ionic bond. It's not really a bond because there's nothing binding the two together outside of electrostatics. The metal loses an electron, becomes positive. The non-metal gains an electron, becomes negative. And the electrostatic interaction between the two is what we know as the ionic bond. The attraction holding them together. Paula Abdul says opposites attract, and this is the attraction between those two. Covalent bonds, the other one that we're usually spitting out when we talk about the two kinds of bonds that there are, represents an atom that has electrons to give, and this one has electrons that wants to take electrons. However, it's not a give and a take, it's more of a share. And so this is the sharing of electrons between two atoms. And that happens at an optimal distance. So the distance at which this sharing occurs is what we refer to as the covalent bond. We can talk about bond lengths in this. And what happens is when this forms, the molecules that are formed from these bonds, they're independent of each other. The lattices that set up here, they're not really independent of each other. Like two salt crystals, they are independent of each other, but these are dealt with in what's called formula units, which is whole number ratios of these metals and non-metals coming together. An atom, a molecule like CO2, any two molecules of CO2 are mutually independent. And this typically happens between two non-metals. There are also metal-metal bonds for alloys. That's kind of out of the scope of this class, but it's one that exists. So this was a question that kind of came up on the quiz. It's something you can expect to see on the test. But when we talk about pure substances, we know that it breaks down into one of two things: it's either an element or a compound, made of just one atom or groups of or atoms in ratios. So if I have just an element, that element is either by itself, like it's atomic. So here, your book's example is neon. So atoms of neon in a gas are independent. Or molecular. So this would be a molecular element, where these are actually no longer in individuals. They are at least in pairs, and there are some that are in more than pairs. So the ones that are commonly in pairs are hydrogen, nitrogen, oxygen, chlorine, bromine, iodine. So basically a hydrogen, and then there's a little L on the periodic table. Those are the molecular diatomic species. All the nitrogen and oxygen that we breathe in our air, making up over 98% of it, these are diatomic. Compounds are things that are combinations of atoms in whole number ratios. So water, H2O, that's an example of that. Sodium chloride, an ionic solid, that's a measure of that. So these compounds can be either ionic or molecular. In some cases, hybrids of the two. But we're going to talk about how we can actually name these. So it's important for us, if you're going to be a chemist or a chemical engineer or a scientist of any kind, that know that there is a way to understand from a formula we can get to a name, and from a name we can get to a formula. Right? That's a very important skill in this field. So every compound that exists should have just one name, and that keeps it from being ambiguous. So if I was to say, hey, somebody give me the sodium chloride, I don't have somebody saying, well, which one? So I want to be clear on it. And every name should only correspond to one compound. And so, again, as to prevent things like ambiguity. So the way we do it, if we're going from a formula to a name, so here's the formula, NaCl. How do I turn it into the name sodium chloride? Well, I state the cation first, and that's the first thing there, the metal or the cation. Its name is sodium, so that goes there for the name. And then I give the anion. Now the anion is the suffix of this nonmetal with an I, is the root of the nonmetal with a suffix of IDE, meaning that it's not chlorine, it's chloride. So sodium chloride. And then all I have to do is state the cation and the anion names, sodium chloride. So this cation here is potassium, this one is oxygen, so it's potassium oxide. This is calcium, this is nitrogen, this is calcium nitride. Okay, so for these, the nice thing about them is one, I know their charges, and two, going from that name to this formula to this name is pretty straightforward. So if I have calcium and fluorine, I would just call it calcium fluoride. Now, going from a name to a formula is a little bit trickier because it requires you to know some stuff. So one of them is sodium bromide, NaBr. Lithium sulfide is the other, aluminum oxide is this. So if I'm going from the name, sodium bromide, I need to know the charge of the cation. So looking on the periodic table, sodium is there in the first column, +1 charge. Bromine is there in that second to last column to the right, it has a -1 charge. So +1 and a -1, they come together in a 1-to-1 ratio. So its formula must be Na and Br coming together. Lithium sulfide. Lithium's got a +1 charge. +1 charge is there in the first column, it's the first of the alkali metals, and then sulfur's got a -2 charge. So a +1 and a -2 come together is not a neutral molecule. I need 2 of those lithiums to come together with 1 of those sodiums, and when they do, then it's a neutral molecule. So I've got a +1 and another +1. And this is a -2, so +2 and -2 cancel each other out. Aluminum oxide, aluminum's got a +3 charge, oxygen's got a -2 charge. So the easiest way for me to do that is to find the lowest common multiple, which is 6. So 2 aluminums and 3 oxygens will make a neutral molecule. So down here, I've got an example of calcium chloride. And to show you how it works, calcium is a +2 and chloride is a -1. So something that's correct would be a calcium and 2 chlorides, because a +2 and 2 -1s add up to 0, that's neutral. Something that's incorrect would be a calcium and a single chlorine, because that would be a +2 and a -1, that is not balanced, that would be incorrect. So that is not calcium chloride, this is. Some general guidelines for this is one, use the periodic table. You should have a periodic table. You should have one actually printed out that you write on. A well-loved periodic table is a very good tool for anyone going through science. And don't come in charges. If you're naming things that contain a metal and a non-metal, using di and tri, you're doing it wrong. So no dis or tris with these binary inorganic ionic compounds. It always involves a metal and a non-metal, and the metal is always named first. So this would never be bromide sodium. That would be simply incorrect. So here's the problem if we're using a binary inorganic compound where the charge is variable. I've got 2 things here, FeO and Fe2O3. The first one's called iron oxide, the second one's also called iron oxide. I can't have that. That's the same name being used to describe 2 different compounds. FeO and Fe2O3 are not the same. So I can't have that. The solution is I need to use the charge in the metal to show that there's a difference between these 2. I have iron here. But this iron's not the same as that. So here's how we figure it out. FeO, that's an iron and an oxygen. And the sum of those two charges needs to equal 0. So of those two charges, I know what oxygen is. I don't know what iron is. It's in that middle part of the periodic table, the transition metals, where things can have lots of different charges. So the sum of those two things has to equal 0. If oxygen is -2, the only thing that iron could be is +2. And so I use a Roman numeral in its name to describe it. So iron 2 oxide is the name of that compound. Second compound, Fe2O3, this works out the same way. I've got 2 irons and 3 oxygens, and the whole thing has to add up to 0. I don't know the charge of my iron, so I'm going to leave that there. I've got 3 oxygens, and I do know its charge, -2. This whole thing is -6, and that has to add up to 0. So the only thing that solves this is making iron +3. So 2 times +3 is +6. 3 times -2 is -6. Adding those two together is 0. And so this is iron 3 oxide. And this number right here in the Roman numerals just tells us how what the charge of that iron is, not how many iron atoms there are. There are 2 iron atoms in this, but we call it iron 3 because 3 is the size of its charge. There's some important exceptions to this, like in the periodic table, parts of it you in the middle where we do actually know the charge of something. So here's an example: aluminum, zinc, and silver. They always have a charge that we know. So aluminum is always +3, zinc is always +2, silver is always +1. Scandium over here is always +3. All of these others have charges that we don't always know, so we kind of have to be specific. So these are the ones that you want to be aware of. So these are all just for cations, by the way. We didn't list the anions. All right. So here's the way you would commonly be asked a question about this. I've got formulas here, you need to get a name, and I've got names here, you need to get a formula. So CaO, you would give that a name. CrCl4, you would give that a name. DNBr2, you'd give that a name. W3 and 4. In class, this would be, like, not necessarily a quiz, although this is very quizable. But I would give you probably like 5 minutes to complete that. Through the magic of the internet, we don't have to take 5 minutes to do this. But I will give you like 1 minute to at least get a start on it. So try to do a couple of these and a couple of these. Now, I did not separate them into what kind of binary nomenclature it is. It's one of the two we discussed in each one. So it'll be about a minute. We should definitely try these. About 15 seconds remaining. Okay, so coming up with answers on this, CaO is calcium oxide. CrCl4 is chromium 4 chloride. The way I know that is chlorine's got a -1 charge, so chromium must have a +4. ZnBr2 is zinc bromide, not zinc 2 bromide. That would be ambiguous, not ambiguous, that would be redundant. We always know charges. W3 and 4, tungsten 4 nitride. So nitrogen's got a -3 charge. That means tungsten must have a +4. Magnesium fluoride, going backwards now. Well, I always know the charge of magnesium is +2. Fluorine's a -1. I need 2 of them, so MgF. Copper 2 phosphide. Phosphide has a -3 charge. So I need 2 of them. Copper has a +2 charge, so I need 3 of them, so Cu3P. Silver oxide, Ag2O. Silver always has a +1 charge, so I don't need it. Silver 1 is not something I would say. and Mn4 oxide. So Mn with a +4 charge, oxygen with a -2 charge, so this would be Mn. That ends that. I'm going to stop the share. One other thing I'm going to share with you really quick before I wrap it up completely is on our web page. So let me go to, oh, stop my share, I'm sorry. Didn't do what I expected it to. Okay, go to week 2. And I'm going to share my screen. Okay, so here we are, week 2. So I've put up these two things under class material. So these are PDFs, and this is, the periodic table is a periodic table. This naming compounds thing is a worksheet that I put together that has a lot of this nomenclature stuff all in one spot. I see a lot of students carrying it around, so I do think it's a thing worth looking at and keeping handy. The 2 videos that have made the class so far, our video that from today is going to go here in the lectures. The PowerPoint from today is right here. And then these and the video will go up, but basically this is Randall-Munroe's. If you were to make a periodic table out of elements from the periodic table, what kind of destruction should you expect? It's really funny. I encourage you to take a look at it. Same thing here with a mole of moles. So Randall-Munroe's take on, if you had 1 mole of moles, my God, that's a lot of moles. Is there room for that on Earth? The answer is no. Okay, so again, I'll stop sharing there. That's kind of the end of content for today. So we'll pick up tomorrow. I'll pick up on Thursdays. We'll pick up actually a little more computation. So I'll make videos for the other 2 kinds of naming, which will include polyatomic ions and molecular compounds and acids. So we'll have those, but then we'll start getting into molar masses, empirical and molecular formulas, and then doing that sort of exercise from the data. Okay? So I hope you guys had a good afternoon. Be good. And don't forget, tomorrow, first SpaceX private launch of humans into space, 4:30 p.m. So sort of look to the east and see if you can see this. This is going to be awesome. Do check it out. It's quite historic. It hasn't happened since the shuttle program in 2011. All right. Take care, guys. See y'all later.